Okay, good afternoon. Let's start. Although it's getting fewer and fewer people, this is a very important week. Many midterm tests will be held during this week or next week. As ST2334 will have the midterm test next week. When? Tuesday evening or next Tuesday evening in the multi-purpose sports hall. Is it? Yeah. Okay. Okay. So yesterday we talked about joint distribution, the marginal distribution, and the conditional distribution. So you have to understand that for a given sample point, you can have more than one random variable related to this outcome or sample point of the sample space. So in order to understand fully about how this two random variable or two or more random variable behaves, we need to know the joint distribution. All right. So the joint distribution basically tells you everything about how x and y behave. And the joint distribution suppose involves a functional form or a table form in some discrete random variables, as well as the range or region for which the joint distribution equal to that functional form. Okay, then we also would like to find out if we are just interested in one of these variables, these random variables. Then we can talk about marginal distribution of one of the random variables in the joint distribution. Then next, we also ask ourselves, so what happens if we have some information about one particular random variable? Will that lead us to have a different view of the behavior of another random variable? So that leads us to the conditional distribution of one random variable given the other random variables. All right. So conditional distribution is it's a little bit more complicated, right? So it's something like this. Why I say it's a little bit complicated? Because just for two random variable case, this conditional distribution of y given x is interpreted as a random variable of one dimension, or that means we have only one random variable. But then we have an x there. Now x, the capital letter X, okay, is not a random, okay, because we already take that random variable equals to a particular value, the little x. So in other words, there are no more random variable x, only random variable y. All right. So this whole thing will be tell us something about the behavior or the distribution of y. Condition or given that x, the random variable x equal to the little x. So it's a one-dimensional random variable. But on the other hand, this expression can involve both y and x. All right. So you have to be careful. In terms of random variable, there's only one random variable, the y here. All right. But the expression for this conditional distribution involves y and x. All right, so now, based on this conditional distribution, all right, suppose this one can be shown equal to f of y. In other words, the whole expression does not involve any x. So, and also the range, this is true for all xy. All right, so what does that mean? It means that the y condition on x, all right, the behavior of this conditional distribution does not involve any x. And in that case, we say that these two random variables, y and x, are independent. So that's what we're going to discuss. Independent random variable is a very nice property. If we know that these two random variables or this set of random variables are independent, then it is very easy for us, or we can construct the joint distribution from the marginal distribution. If you recall, yesterday we talked about this f of xy the joint distribution is equal to the marginal distribution times, the conditional distribution times the marginal distribution. This is only one form of it. All right? So this is always true. But if this one can be expressed just in terms of y, then the joint distribution can be obtained with the knowledge of each in the behavior or the distribution, the marginal distribution of each of the random variable. So we don't have to know the conditional distribution. It's too complicated for us because it depends on x. But now we're saying that, okay, it doesn't matter. The joint distribution only depends on each individual marginal. All right? So the x and y have no, they are independent. So the joint distribution just equal to the product of the marginal distribution. So that in that case, x and y are independent. So that's what we are going to discuss. Okay, so we say that the two random variables are independent if and only if the joint distribution is equal to the product of the two marginal distribution. This applies to both discrete and continuous random variables. And this is true not just for one particular xy value, but it has to be true for all xy values. All xy values. So you compare with this one. So this statement, in fact, is the same as saying that, all right, f of x given y, xy, is equal to f of x. Or f of y given x is equal to f of y. What does it mean? It means that the conditional distribution of x given y is the same as the marginal distribution of x, which means that we don't bother, we don't care about what y behaves. So the conditional distribution, all right, is the same as the marginal, which means that x and y are independent. So we can extend this to more than two random variables. If we have a set of random variables x1 up to xn, if we say that they are independent, all right, then that means that joint distribution, the joint distribution, all right, is equal to the product of the marginal distribution for each random variable for all the possible values of xi. All right. So in other words, if they're independent, then this is true. If you have this result, then we conclude that this set of random variables are independent. So that's what we mean by if and only if. So on one hand, if we know that x1 up to xn are independent, then we have this property, the joint distribution equal to the product of the marginal distribution. On the other hand, if we have the joint distribution so equal to the product of the marginals for all xy or all x1 up to xn, then we conclude that x1 up to xn are independent. All right? But I have to remind you that when we say that they're independent, you also have looked at the product space. Well, what does that mean? It means that, okay, if I look at the marginal of x for all x in A1 and margin of y for all y in A2, then we have to look at the product of this one true for all xy, for all the point xy in the A1 times A2. So it's something like this. So if the marginal of x is defined over this region, between A and B, let's say. So this is my A1. While the PDF of y is defined between C and D. This is my A2. So the product must be positive over this region. Over this region. This is the A1 times A2, the product space. So it's a rectangle. You see, A1 is a part of a straight line. A2 is part of the R, part of the real line. So the product space will be a rectangle. So In other words, the above definition, when we say f of xy is equal to f of x times f of y, is true for all the xy in the product space A1 times A2. If A1 is the real line and A2 is the real line, then the product space will be the R2 plane. All right? Okay, here is an example. This is for discrete random variable. So we have this John distribution, x and y. X only takes two values, 2 and 4, and y takes the value 1, 3, and 5. All right? So we have shown that the marginal of x, that means for x equal to 2, I have to add up all the probability function for x equal to 2. So x equal to 2, y equal to 1 is 0.1, x equal to 2, y equal to 3, the probability is 0.2, and so on. So the marginal of x is 0.4 when x equal to 2, 0.6 when x equal to 4. Similarly, the marginal of y is given by this. All right, when y equal 1, the probability is 0.25, y equal to 3, probability is 0.5, and y equal 5, the probability is 0.25. All right, so this is the John PDF, and we work out the marginal as well. So we are asked whether x and y are independent. So follow from the definition, we have to check the f of xy. For example, f of xy 1, 1. So this one, according to what we are given, it is 0.1. Then what is fx1? Sorry, 2. X has to be 2. 2 and 1. So f of x1 equal to 0.4. How about f of x2, sorry, f of x2 equal to 0.4. F of y1 is equal to 0.25. Then the product of these two equal to 0.1. So in other words, f of xy equal to f of x, f of y, when x equal to 2 and y equal to 1. So at least for this point, it's correct. But you cannot jump to the conclusion that x and y are independent. You only have to check one point only. You have to check all the possible combinations. So you have to check the rest. Altogether, there are 6 possible values. So you check all this. So we shown here. All right. So all the 6 points seems works. The product of the marginals equal to the John distribution for all the 6 points. All right. Then how about this? X equal to 2, y equal to 1. That's y equal to 1, 3, 5, 7. What is this? And what is this? Do you know this value? X equal to 2, y equal to 7. X equal to 2, y equal to 7. Y is not part of the value with non-zero probability function. So that means it is 0. Outside all this, it is 0. So this one is 0. All right. How about this? F of y 7. This part is also 0. Although this one is 0.4, right? 0.4. So it still holds. So basically, all right, my point is you just have to check for those x value for which the marginal, you have to check all the x value for which f of x is bigger than 0. You don't worry about f of x equal to 0. In other words, I don't have to check x equal to 1 or x equal to 10 because I have only 2 values, x equal to 2 and 4 only, that have bigger than 0. So you also have to look at the y value for which this one is bigger than 0. So in this example, this means that you only check x equal to 2, 4, all right, and y equal to 1, 3, 5. You just check all this. 2, 4 means 2 outcome of 2 possible values for x. y has 3 possible values, so altogether it has 6 possible values. You have to check all these 6 possible values to check what? Check whether this statement is correct. The marginal equal to the product. Sorry, the product of the marginal equal to the John distribution for all xy. All right. So what happens if I find one particular xy such that this f of xy does not equal to fx times f of y? Then what happens? That means this is not true for all xy. Maybe I can find one xy such that this is not true. This is not true. Then the conclusion is that x and y are not independent. All right. So in other words, checking not independent sometimes is easier. If you're able to find one particular xy values such that f of xy does not equal to fx times fy. But in this example, yes, xy are independent. So what does it mean? So basically you can look at it. You look at it, all right? You sort of like, now, let's look at y. So y, the probability is 1/4, 1/2, 1/4. So in the ratio 1 to 2 to 1, right? 1 to 2 to 1. Now then you look at when x equal to 2. All right? The behavior of the probability is also in the ratio of 1 to 2 to 1. Not only that, you look at when x equal to 4. The value, the probability of x when y equal to 1, y equal to 3, and y equal to 5 is also in the ratio of 1 to 2 to 1. 1 to 2 to 1. So it means that no matter what your x value is, the probability function of y equal 1 or 3 or 5, they are of similar behavior. So it's in the ratio of 1 to 2 to 1 in this case. So it behaves the same. So that's the idea of independence. Now if you look at y, all right, so I fix y and look at this, all right, so the ratio is 2 to 3. So you look at this one, also 2 to 3, look at this one, also 2 to 3, and look at this one is also 2 to 3. So in other words, it doesn't matter what your y value is, the proportion of the probabilities of x equal to 2 relative to x equal to 4, they are in the same ratio. So that's the idea of independence. All right. All right. So let's look at another example. This is an example without a table. So we are given the John distribution equal to xy over 36. And this formula is only valid for x equal to 1, 2, 3 and y equal to 1, 2, 3. So altogether, there are, according to the description, there are altogether 6 possible xy. 3 times 3. So, sorry, 9 possible xy values. So you have to check all this. All right? But it's a bit troublesome if I have 1, 2, 3 and 1, 2, 3. So what happens if x has 1 up to 10 and y 1 up to 10? Wow, I have 100 points. Do I have to check all this 100? All right. So we try to work systematically. So in other words, now I try to get f of x. I think we have done this before. So this one turned out to be x over 6. And f of y, you referred back to this example, I think on page 312. So it's y over 6 for x equal to 1, 2, 3, and for y equal to 1, 2, 3, and 0 otherwise. So in other words, now I try to do a general way. So I work out the marginal of x and marginal of y. So marginal of x is x over 6, and marginal of y is y over 6. For x equal to 1, 2, 3, and y equal to 1, 2, 3. So in other words, now I check f of x, y is equal to the product of these two. For x and y, for x equal to 1, 2, 3, and y equal to 1, 2, 3. Which means that x and y are independent. All right, so this is f of x, and this is f of y. All right, so f of xy is equal to f of x times f of y. All right. So, and it's true for, this is important, it's true for all x equal to 1, 2, 3 and y equal to 1, 2, 3. So it's in, x and y are independent. Okay? Now let's look at another example. This time is for continuous random variable, and we are told that these two random variables x and y are independent. All right. So we are given that they're independent, and we are given that f of x equal to e to the power minus x for x greater or equal to 0. All right. And f of y e to the power minus y when y is bigger or equal to 0. Then what is the John distribution? So according to properties of independent random variables, then this one is equal to f of x times f of y for x bigger or equal to 0 and y bigger or equal to 0. So, and this one is equal to e to the power minus x minus y, or e to the power minus x plus y. All right? So this is the John distribution over this range. This is the product space. And why we can do that? Because we are told that x, y are independent. Without this, you cannot just multiply the f of x and f of y. All right. And don't forget, when you multiply, you also have to consider the product space. That means the x range for which f of x is bigger than 0, and also the y range for which f of y is bigger than 0. So you combine these two to form a product space. Okay, so here's another example. F of xy equal to 2 times x plus y over this range. All right? Now this is not a rectangular range. All right? So it represented by this triangle. How to get this region is basically you look at these 4 inequalities. Okay, if you want, you can put an equal sign. It doesn't matter for continuous random variable. All right. So this basically 4 lines, and the region bound by these 4 inequalities. All right. So x bigger than 0. This is x bigger than 0. Bigger than 0 means this part. X less than 1. This is x less than 1. This is x equal to 1. So x less than 1 is on this side. So in other words, these 2 inequalities give us the area between these 2 lines. Then y has to be bigger than 0. So this is y equals 0. Bigger than 0 means this one. And the last one is y less than x. So you are looking at the line y equal to x. All right. So this is the line y equal to x. And y less than x. So you have to decide which part, which region. So if you consider a point here, for this y, okay, take a particular point. Y equal to 0.8 and x equal to 0.2. So in this case, y is bigger than x. So it does not satisfy this. So in other words, this is not the region that we want. This is the region that we want. So let's come up with this triangular shape. It's important that you have to identify the region, maybe have some idea what the region look like. If you are not very good at because later on when we do the integration limits, how to figure out the integration limit, you have to know how to get it based on these inequalities. But if you are not familiar with, you better right from the start, from the beginning, when you look at this region for which the John PDF is bigger than 0, you have to draw the picture. All right, so x, y independent. So basically what we need to do is to do the following. First of all, get the marginal of x. Second, get the marginal of y. Remember, when you get the marginal, you have to get the region for which the marginal distribution defined. Then check whether it's equal to the product. F of xy equal to fx times f of y. But without doing much work, I can tell you x and y are not independent. How do I know that? It's very simple. Okay, what is f of xy for this point? 0, right? Because only for this region, then f of xy is given by this expression. Outside that, it is 0. So this point is 0. But what is f? Okay, in other words, I'm looking at this point. X equal to 0.2 and y equal to 0.8. All right? What is f of x at 0.2? Of course, you can do it and work out what is it. But basically, it is to try to sum up or sum up all the density here at this, so that you squeeze all the density at this point. It is non-zero because you have a positive density. So this one is bigger than 0. Similarly, this one is also bigger than 0. So for y equal to 0.8, you have to squeeze all the density here onto this point. You squeeze all the density with the same y value. So you basically squeeze all the density along this line, y equal to 0.8. So it's bigger than 0. But what is the John distribution of 0.2 and 0.8? It's equal to 0. So two non-zero value cannot have a product equal to 0. So obviously it will not satisfy. But what's the trick? Basically, because of space, the John distribution does not have a rectangular space. So it makes the life easier. Because it's not rectangular, so I just find a point for which the John distribution equal to 0, but the two marginal distributions are non-zero. All right, so I know the answer. So now I try to do it formally. So in other words, I try to work out the margin of x and margin of y. So the margin of x, I have to integrate y. All right, so the John distribution, remember, is only valid for this part. So now I integrate y, means that I have to fix x. All right, I fixed x, fix the x value. Then what is the y value here? The y value is 0. What is the y value here? Y value equal to x. So it's from 0 to x. All right, over the range from 0 to 1. From 0 to 1. So that's how you got it. So I left the integration for you to complete. So the answer is 3x squared for x between 0 and 1. So similarly, the marginal of y, so in this case, so I want to integrate x, so I have to fix y, fix a y value. So the x value here, x equal to y, and at this point, x equal to 1. So the integration limit is from y to 1. All right, so you try to integrate all the density over this line, this part of segment. And this is valid from 0 to 1. All right, 0 to 1. Y between 0 and 1. Outside that is 0 because there's no density. For any y value outside 0 and 1, the density, there's no John density. There's no John probability density. So it's 0. So after you complete it, it is 1 plus 2y minus 3y squared. All right? So now you look at it. So this is my John distribution. This is the range. And this is my marginal equal to this for this region. So it seems obvious to me. How can you multiply these two to get something like that? All right. One involves x, one involves y. When you multiply them, how do you get x plus y? You won't get x plus y. So in other words, f of xy does not equal to f of x times f of y. All right. So at least for some of x, some x and y, and so we say that x, y are not independent. All right. But you can just use the method that I mentioned. I choose a point here. Remember, these are the John PDF. I choose a point, any point here, convenient point, and then work out what is f of xy and what is f of x and f of y, and show that they are not the same. So long as you can find one point, at least one point, that f, the John probability density function, does not equal to f of x times f of y, then x and y are not independent. All right? Okay. So, so this is what I just mentioned. So it's x 0.6 and y 0.8, then they are not the same. So this may be easier, all right? But if the John distribution is over a rectangular shape, it does not mean that x and y are independent. We just still have to check for all the points here whether this is correct. Whether the product of f of x and f of y equal to the John PDF, whether this is correct over the region here. All right? So what I'm saying is that if the region is not rectangular, it's not a rectangular shape, then it's almost sure that they are not independent. They are not independent. But if there's a rectangular shape, you cannot jump to the conclusion that, oh, x, y are independent. No, you still have to check, all right, whether x, y, f of x, y equal to fx times f of y. All right? Now here's another example. I have this rectangular shape, all right? X between 0 and 2, and y between 0 and 1. All right? So are they independent? So I have to work out what is f of x and what is f of y. So for f of x, so long as x between 0 and 1, then the marginal of x turn out to be x over 2. All right? Similarly, f of y, so I integrate the John PDF for x, all right, from 0 to 2, when y between 0 and 1, and it turns out that it is 2/3 times 1 plus y. So now I look at the product. All right, look at the product. What is f of xy? Okay, f of xy. F of xy is 1/3 x times 1 plus y. All right, 1/3 x times 1 plus y. All right. While our this is f of xy, and our f of x is equal to x over 2, right? X over 2. X over 2. And our f of y is equal to 2/3 1 plus y. Then you can see that the product of these two will give you this one. Okay, so the John distribution equal to the product of the two marginals. Not only that, the space is a rectangular shape. So the region for which this John distribution equal to this expression, in fact, comes from these two components. The x region for which this is defined, and the y region for which this is defined. So in other words, basically, we are saying that, okay, x between 0 and 2, the marginal of x will define as this one. Outside it, it is 0. And then for y, it's valid for between 0 and 1. So in other words, this part of the y value, the marginal equal to this expression, and this part of x value, the marginal equal to this expression. So now the product of these two region, it gives you this rectangular space, and the John PDF equal to the marginal, product of the marginals. So x, y are independent. The random variable x and y are independent. All right? Now, how about this example? Oh, so we also a rectangular shape. X between 0 and 1 and y between 0 and 1. And the John distribution equal to x plus 3 over 2y squared. So we just routinely try to calculate f of x, which turned out to be x plus half, and over this region, x between 0 and 1. And f of y, it is half times 1 plus 3y squared over this region. Then what we have to look for is whether f of xy equal to f of x times f of y. All right? So what's our yeah, okay. So the John distribution, yes. So it's this one is x plus 3 over 2y, while this f of x is x plus half, and this one is half times 1 plus 3y squared. So obviously the product of these two does not give you x plus 3 over 2y. All right? The product of these two factors, one involves x, one involves a y. So the product will not give you a factor which involves the sum of x as a linear combination of x and y. All right, so they are not equal. Now, sometimes it's a bit tricky to show they are equal. Basically, you have to think of it this way. Whether this John PDF can be factorized or not. So for this particular John PDF, you cannot factorize. So John PDF is equal to one factor, which is x plus 3 over 2y, only one factor. On the other hand, the product of f of x and f of y is two factors, and then no way, or you can multiply it out and find they are not equal. Obviously, there's a y square here, but there's only y here. So it cannot be the same. All right? But sometimes, for example, maybe the John distribution is like this. Then this one can be written as x plus y, something like this. Although this is still not, what I mean is that you have to worry about can you do the factorization of the John PDF. All right? So this one, obviously, you cannot factorize it. But this one, that you can factorize it. Or maybe, yeah. Maybe something like this. Then it's obvious. So now, it's 2x plus xy can be factorized as x times bracket 2 plus y. So then may be a possibility that it's equal to the marginal of f of x times f of y. So what I'm trying to say is that you try to look at whether you can factorize your John distribution. All right? Okay, so now we have covered John distribution, marginal distribution, conditional distribution, and then for conditional distribution, we can look at whether the random variables are the same or not. So in other words, for independence, so x, y are independent. By definition, is f of xy equal to f of x times f of y. All right? For all xy. But you can also have f of y given x equal to f of y. Or f of x given y is equal to f of x. These three identities are equivalent. One implies the others. Why? Because you think of it, this is always true. F of xy is equal to, you want both to occur. So let's do it step by step. First, I let x happen, x equal to little x. Then I consider the chance of y equal to the random variable y equal to little y, given that x equal to little x. This is always true. All right? So if this is correct, then I replace this by f of y, the margin of y. So in other words, with this one, I can work it out, it's equal to this, because I replace this by f of y. So the John distribution equal to the marginal. Similarly, I can write this as, I can write f of xy as, this time I work out the y first, and then look at x given y. So with this, I replace this by the marginal of x. So again, I will have this one. So these three identities are equivalent. What does it mean? It means that you can look at it when we say x and y are independent. It's basically saying that the conditional distribution of y given x is the same as the marginal of y. Or the conditional distribution of y given x is the same as the marginal of y. All right? So now we move on to talk about expectation. All right? Why we need expectation? Now, expectation is a number, one number. It's not a random variable. And this number tells us sort of to summarize the behavior of this distribution. The distribution tells you everything about how this random variable behaves. So basically, it tells you what are the values and how likely the random variable take that value. That is the idea of the distribution. Well, expectation is to sort of where the center is, where is the most common value for this random variable. So we extend this idea of expectation to John distribution. So in fact, what I wrote down here is a very general type. It's a function of two random variables x and y. And what is the expectation? What do you expect about this value, this function? So follow from the idea of, or the definition of random variable, is this function times how likely this function takes the value lead to x, lead to y. And then I sum up for all the possible y and x value. That is for discrete random variable. For continuous random variable, I multiply the function gxy with respect to the PDF, and then try to integrate from -infinity to infinity for x as well as for y. For our module, it doesn't matter whether you integrate x first or y first. But from practical point of view, sometimes the integration order may make the integration easier to work with. So you have to figure out which one is easier. But it doesn't matter. You just do a longer, the order is, if you consider dy dx, you should get the same answer. But it depends on the John PDF. So as well as the gxy. So sometimes a particular order may have an easy way to work with. All right. So can the gxy equal to x? Is x a function of xy? Yes. Yes, it's a function of xy. All right. So from this point of view, you can find expectation of x. Given that you know the John distribution of xy, you can find expectation of x. All right, you just replace this by x. All right. In fact, it's not too difficult to see. If I replace this by x, so basically I'm summing over y, summing over x, summing over y, x times f of xy. All right. Okay. I'm going to multiply x to all the John probability function, sum over y, then sum over x. But as you can see, when I sum over y, this one is a common factor. For different value of y, it's always have this same x. So I bring it out. So it becomes summation x, x times summation y, f of xy. But what is this? What is sum of the John distribution over y? That is the marginal of x. Marginal of x. So this becomes f of x. So basically you are summing x times f of x. So that's what you get, the expectation of x. All right. So what I'm trying to tell you is that if you are asked, or you're given a John distribution of x and y, and you are asked to find the expectation of x, there's two ways to look at it. One is treat this x as a function of xy. So you just apply this definition to get the expectation of function of xy. Alternatively, because your interest only in the expectation of x only involve x, so it's naturally you ask, okay, I don't need the John distribution of xy. I just need to know the marginal distribution of x. So you work out the marginal distribution of x first, and then get the expectation of x from the marginal of x. So it will be the same answer. All right, so a particular case is when this function equal to x minus mu x and y minus mu y. Remember, expectation mu x is the expectation of x, y is the expectation, mu y is the expectation of y. Now this function, the expectation of this function has a name for it. It's called covariance of x and y. This quantity tells us expectation of x minus mu x times y minus mu y, tell us how x and y behave jointly. So basically, it simply tells, okay, look at, for a particular value of xy, you look at how far the x different from the center, and how far the y different from the center, and then look at how they behaved. All right. So that is the idea of behind this function. What is the expectation of this quantity called? That is the variance. All right, the variance. All right, that is to measure each in the difference between x and the center, mu x, and then square the difference and look at how we expect this value. Okay, that means this quantity is weighted by the probability density or probability function. All right, so this is called covariance. All right, it's expectation of x minus mu x and y minus mu y. Because this tells us something about how x and y behaves. Now, if covariance of xy equal to, let's say, 100, what does it mean? Compare with covariance of xy equal to minus 100. In other words, what I want to ask is, okay, how to interpret covariance being positive or covariance being negative? All right. So you can think of it like this. So if you have a positive covariance, so that means okay, when you get positive, you expect a positive number. So in other words, that means x minus mu x and y minus mu y must of same sign. That means if x is below mu x, you expect y is also below mu y. All right. If x is bigger than mu x, you also expect y bigger than mu y. So it is either two positive number multiply or two negative number multiply, most of the time, not always. All right. So then that will give you a positive number. But negative number means what? Means that the product is likely to be negative. That means one is a positive value, the other is negative value. That means if x is bigger than mu x, you expect y is less than mu y. So they go in different direction. X, y behaves differently. All right? So you can think of it. If you see a positive covariance, it means that when x increases, y also increases. All right? They go in the same direction. But if you see a negative covariance, then that means if x increases or one variable increases, the other variables decreases. You can think of it like this. This is just to give you some idea. So for example, you have points like this. Okay, so the center is somewhere here. So you can see that the points is bigger than, for x, this is bigger than this one. At the same time, the y value is also bigger than mu y. So that's why for this point, the product of x minus mu x and y minus mu y is positive. For this point also, because the x value is less than mu, this is mu x mu y, for example. All right. So this x is less than mu x. At the same time, y, the y value is also less than mu y. This is xy. So y is less than mu y, x is less than mu x. So the product will be positive. So the positive covariance tells you that the xy are going in the same direction. On the other hand, if you have something like this, then in that case, if this is the mu x, mu y, you can see that for this particular point, the x value is less than mu x, but the y value is bigger than mu y. So that's why the product becomes negative. Similarly, for this point, the x value is bigger than mu x, but the y value is less than mu y. So the product of x minus mu x times y minus mu y becomes negative. So this will indicate that there is the covariance is negative. Okay, so that's how we interpret it. So if covariance is positive, means that xy goes in the same direction. But if covariance is negative, that means the behavior of x and y are in opposite direction. If x increases, y decreases. All right? But we cannot tell from the magnitude. We only can tell from the sign. So the magnitude depends on the scale of x and y. So we come up with this, okay, this is how we get the discrete case, how to evaluate the covariance xy. And for continuous case, we do the integration. All right? Now, so this is a working formula. This is a working formula. Expectation of xy is equal to expectation of xy. This is a function of x and y. This function is the product of x and y, then minus mu x times mu y. If you recall, the variance of x, we have this formula. It's similar to this formula. All right? The idea is the same. All right. But if you want to get the covariance, either you work on this x minus mu x times y minus mu y, which may be troublesome, but you can also work on this, the product of xy, and the minus mu x, product of mu x and mu y. So either way will give you the covariance. And if xy are independent, then the covariance of xy equal to 0. All right? It's not too difficult to show that the covariance equal to 0. If xy are independent. But the converse is not true. All right? So xy independence implies covariance xy equals 0. But when covariance xy equals 0, it does not imply xy are independent. All right? So it goes in one direction. So in other words, independent is a stronger property. So if you have two random variables, which we know that if they are independent, then we can say that the covariance of xy is equal to 0. But on the other hand, if we only know that these two random variables with the covariance equal to 0, we cannot conclude that the xy are independent. All right? And the covariance for ax plus b, so this is a random variable, this is another random variable. So the covariance of these two random variables is equal to AC times the covariance of xy. So in other words, if you create a new random variable or two new random variables by multiplying the first one, x, with a and then add a constant. And the second random variable that you create is multiply y by c and add d. Then the covariance of these two new random variables is the same as AC times covariance of xy. So in other words, only when you multiply by a scale, by a factor, it will change your covariance. All right? But adding a constant to a random variable will not have any impact on the covariance. All right? So what is the covariance between ax plus b and y? What is the covariance of this one? So it's equal to a times covariance of xy. All right? This one just c equal to 1 and d equals 0. But in fact, it doesn't matter what constant you add to the random variable. Adding a constant to a random variable you create a new random variable. But how does this new random variable behave? So first of all, we know that the variation will not have any impact by adding a constant. So for the covariance also, adding a constant will not have any impact. Now this is more important. I don't know whether you remember variance of ax plus b. This is still one random variable. I create a new random variable, I call it ax plus b. It's a random variable. Why? Because it depends on the random variable x. A and b are constant. So this one is equal to a squared times variance of x. So in other words, if you create a new random variable, by multiplying the random variable with a and add a constant b, then you only change your variance to a squared times variance of x. The b will not involved. Okay, this formula applies to a new random variable, which is the sum of two, or a linear combination of two random variables. Compare with this one. This one you still have one random variable. The other term b is a constant. All right. But while if you have sum of two random variables or a linear combination of two random variables, then the variance of it is equal to a squared times variance of x and b squared times variance of y, and you have this extra term, all right, which is 2ab times covariance of xy. So in other words, the behavior of this new random variable, all right, these two random variable, or ax plus by, this new random variable, consists of part from the related to variance of x, related to the variance of y. On top, there is an extra term, is the how xy related, how xy jointly behaves, the variation. So you need to have this covariance of xy. This comes from the idea that if you have two, because variance basically is the expectation of square of this minus the expectation of this quantity. So it's a square, expectation of square. So when you expand the square, you have s squared plus t squared plus 2st. So the covariance is come from this one. When you do the when you expand it, all right. I don't want to go into the details of the proofs, but just let you aware of that. When you look at the look at the variance of the sum of two random variables, or linear combination of two random variables, then the variance of this linear combination of random variable is equal to a squared times variance of x, b squared times variance of y. But don't stop there. You have 2 times ab times covariance of xy. So you think of it, if I asked, now if x, y, the covariance is positive. The covariance is positive. All right? So I create this ax plus by. I have an option to choose a and b, or at least the sign of a and b. I can have a, b are both positive, or a, b are of different sign. All right? So now, let me ask you, I want to create a new variable, which is ax plus by. I want the variance of this new random variable smaller as possible. So should I choose a and b of the same sign or of different sign if the covariance of xy is positive? Let me repeat my question. I have an option to choose A, B. Either A, B are both positive, or A, B are of different sign. Or A, B are both, okay, let's simplify it. A, B of the same sign. So maybe positive or negative. All right? and A or B are of opposite signs. Only these two choices. Right. So A, B are both same sign, or A, B are of opposite signs. One positive, one negative. All right? So I have these two choices. So now my objective is to, one more thing I forgot to mention. Let's say the covariance of XY are positive. All right, then I ask you, should I pick A, B of the same sign or put it as opposite signs? So that the variance of AX plus BY is relatively smaller for a fixed magnitude. Okay, so what can we say about this term? This term is always positive. This term is always positive. A squared is positive, variance of X is positive, B squared is positive, variance of Y is also positive. Because it doesn't matter whether A is positive or negative, A squared is positive. Then this one, I already said covariance of X is positive. How about this? Do we need A and B of the same sign? If of the same sign, then it will be positive. So the whole thing, you have A square variance of X, B square variance of Y. They're already there. You cannot touch. There's no way that you can change them by choosing the sign. But then how about the third term? It's 2AB times covariance of XY. All right? XY, covariance of XY is positive. So now I can choose the AB. If I choose AB of the same sign, either both are positive or both are negative, I will have a positive term. But if I choose A and B are of opposite sign, then what is the sign for AB? Product of AB. It will be negative. So negative, so that means the third term will have a negative coefficient. So in that case, I reduce my variance, right? So, so what happens if the covariance is negative? Then I have to choose the same sign. All right? I have to choose the same sign if the covariance is negative. So my point is, sometimes, you're given the expression like that. We can prove that. But you have to know this will lead to the understanding of how the choice of your A and B will affect your variance of AX plus BY. All right? It also depends on the covariance of XY, whether it's positive or negative. All right. So, in fact, this is something to do with finance. When the investor portfolio, I look at the portfolio. So AB is the proportion. Okay, I have two. X represent the return of the stock A, Y represent the return of the stock B. I want to minimize the variation. All right. So whether I can choose the A and B, which are the proportion of stocks that I want to buy. So they must be positive. So if I want to minimize my risk or minimize the variance, I have to choose the stock X and Y, which are go in opposite direction. That means they behave in the opposite direction. So if one increase, the other one will decrease the returns. So in that case, it will be safer. Your variation will be smaller. All right. So that's the idea used in investment portfolio. A very simple idea. Okay, I don't want to go into that too much, but I just want you to be aware of how to get the variance of a linear combination of two or more random variables. Okay. So just now I mentioned the covariance of XY, positive or negative, we understand that. But the magnitude itself does not tell you anything. So what I mean is that covariance XY, all right, equal to 100, and covariance of UV equal to 1 million, all right? So which one has a bigger covariance, sort of closer or a stronger relationship. Both are positive. So we know that x goes up, y goes up. Or x goes down, y goes down. But how do I know which one has a stronger relationship? So we cannot tell. You may think, oh, 1 million so big compared with 100. Of course, 1 million is bigger. But this number depends on the scale of x and y. So maybe x and y, the x magnitude is in the range of millions. Y also in the range of millions. So of course, then your covariance of xy will be big. All right. So what I'm trying to say is that you cannot just look at the magnitude of the covariance, because the magnitude will depend on the scale, or the magnitude of x and the magnitude of y. Oh, sorry, covariance of uv. U is in the range of million. V is also in the range of million. So no wonder the covariance of uv is in the range of million. All right. So to compensate for that, so we try to take into consideration the scale of x and y. So we adjust by the standard deviation, or the standard deviation of x and the standard deviation of y, which is what as try to normalize the impact of the magnitude of x and y. So after we adjust, divide by the standard deviation of x and the standard deviation of y, then this number will be between 0 and between -1 and 1. This, we call it correlation coefficient. Let me repeat it. Covariance of xy only tells you how they behave, whether they go in the same direction and go in the opposite direction. But it does not tell you how strong the relationship between x and y, because the magnitude depends on the figures or the value of x and y. All right? The two random variables. So in order to fix this problem, we consider of adjusting the scale. So we divide it by the standard deviation of x and the standard deviation of y. And by doing that, we come up with a number, a quantity, which does not depend on the scales or magnitude of the x and y. So it has to be between 1 and -1. And this is called correlation coefficient of x and y. Okay, it's between 0 and 1. And this quantity, in fact, used quite often, measure, I have to stress, measure the degrees of linear association between x and y. All right. Now, sometimes the two random variables are related, but not in a linear sense. All right. For example, if y equals x squared, they are perfectly related. But if you work on the correlation coefficient, it may turn out that it's equal to 0. So my point is this correlation coefficient only measures linear association. So what I'm saying is like this. Although it's not strictly not correct, but I just give you this picture. All right? So this one, I mean, for us, do you think x and y are related? Yes, it's something like this. But if you work out the correlation coefficient, it may turn out to be a number very close to 0. All right? Because correlation coefficient is measured the straight line correlation. And it turns out that the relationship may be just a horizontal line. That means it's not positive, not negative. All right? So it measures a linear relationship. And if x, y are independent, then this implies the covariance of xy is equal to 0. This implies the correlation coefficient equal to 0. But on the other hand, correlation coefficient equal to 0 does not imply independence. All right? Okay, here is an example. So this is the John PDF. Okay, so we work out the covariance. Okay, work out expectation of y minus x, covariance of xy, and correlation of xy, and the conditional expectation of y given x equal to 1. So this one is the function, this is a function of xy. So it is y equals 0 minus x equals 0. And the probability of y equals 0 is 1x. And this one is f of xy with y equal to 1 and x equal to 0. So it's y minus 0, y minus 0, minus x. So it's 1 minus 0. And the probability is 1/4. So we work on for all these 8 possible values. It turns out to be 1. So this one is to make, the way that I compute it is based on y minus x times the John PDF and evaluate at y and evaluate at x. All right? But there's another way to do it. This one is just expectation of y minus expectation of x. So we can get this from the marginal of y, if you have already worked out the marginal. So this one is worked out from the marginal of x. So this may be easier if you have already worked out the marginal of x and y. So in other words, you can either treat this as a function of xy and then work on the John distribution, or you can treat it as a marginal distribution. But you can do it like that, but this one is not true in general. Here, okay, it means that we look at we do the sum or the difference between y and x, then take expectation. All right, do the sum first or do the difference first and then take expectation. It's the same as take the expectation of each individual term first. Take the expectation of this one and take the expectation of this one. Then we do the subtraction. So it's okay. But this is not true. That means you do the multiplication of 2 random variables first and then take the expectation. It's not the same in general. It's not the same as taking the expectation first and then multiply the 2 expectations. This is not true. Okay, so how about, now this one, expectation of xy, there's no shortcut. You have to do it like this. Sum over x, sum over y, xy times the John PDF of xy. So it's x equals 0, y equals 0, and then times f of xy equal to 0, 0, and so on. So it turned out to be 1. And expectation of x equal to 0.5, expectation of y equal to 1.5. So the covariance turned out to be 0.25. So it's positive. That means x and y behaves in a similar way. That means if x is bigger than mu x, then y is likely to be bigger than mu y. All right? And how about variance of x? So we work out the variance of x is 0.25, variance of y is 1.5 square. Oh, sorry, 0.75. Okay, so the correlation coefficient equal to the covariance of xy, all right, which is equal to expectation of xy minus expectation of expectation of y, so it's 0.25. So it turns out that the correlation is 0.5774. So this at least shows something about how xy are related. So they are not very strong. We expect, if it's strong, expect maybe 0.8 or minus 0.8, then we consider it strong. It's close to 1 or minus 1, then it's considered strong. Here it's about 0.6, so it's a moderate related linearly for this x and y. All right, so the conditional distribution of y given x. So what we have to do, you have to find the conditional distribution. So which we've already done it. So we just applied it and got this. All right. So this is the conditional distribution. So the conditional expectation is 1 times 1/4, 2 times 1/2, and 3 times 1/4. Add them up, so it's 2. So in other words, if x equal to 1, we expect y should be equal to 2, which is different from, if you go back to look at expectation of y that we just worked out, it's equal to 1.5. All right, expectation of y equal to 1.5. So the point is, all right, expectation of y is equal to 1.5. Expectation of y given x equal to 1 is equal to 2. So in other words, with the information that x equal to 1, we expect a higher expected value of y, which is, in this case, is 2. All right? But if you don't have the information about x, you have to consider all possible x and y combinations, then the expectation of y equal to 1.5, which is smaller. So this information of x equal to 1 tells you something about y, which makes the expectation of y value change from 1.5 to 2. All right? So here's another example. It's on continuous random variable. So we're given a John distribution, find the covariance of xy and the expectation of y given x. So it's the same thing. So first of all, we work out the expectation of xy, which is to integrate g of xy times the John PDF, x and y. All right? So we complete the integration, the expectation of xy equal to this. We also have to work out what is the expectation of x and expectation of y. All right? So this are the two expectations. So the covariance is equal to expectation of xy minus expectation of x times expectation of y. So it's equal to minus 1 over 162. So it's a negative number. But is it considered big or small? We cannot tell unless we work on the correlation of xy. That means we work on this one. Then see whether compare with minus 1 to 1. See how big the magnitude. All right. How about the conditional distribution? We have already worked it out on page 358. So this is to, I think, the expression that we have for this one is for f of f, the conditional distribution of f of y given x is 3x plus y over 6x plus 2. All right? For y between 0 and 2. And x has to be between 0 and 1, I think so. All right? So you just substitute x equal to 0.5 into the expression, and then you will get this conditional expectation. All right? Is there any x here in this expression? No x, huh? So can I say that f of x, f of conditional expectation, can I say y and x are independent? No x, huh? Of course no x, because I substitute x equal to 1/2. Of course you don't see x. The conditional distribution is given by this expression. All right? I use this expression by substitute x equal to 1/2. So that's why you don't see x there. All right? So be careful, huh? So this is, I already specified x. So it's now you don't see x. And it's right because now you make use of the information of x. So you don't see any x anymore. So it just depends on y. So I work out, this is how y, the random variable y behaves. The density function depends on the value of y through this function, so long as y between 0 and 2. So the expectation of y, given x equal to 1/2, so you just integrate y, multiply the PDF, and then do the integration. So the answer is 17 over 15. All right? Oh, okay. So we finished chapter 3. Chapter 4. Do you have the notes for chapter 4? Okay, from chapter 4 on, chapter 4, special probability distribution. So we discussed about random variable. We discussed about John distribution of random variables. Okay, so we represent it by f of x, f of y, or f of xy, basically a function. So now, what we are going to discuss are the following. We look at some real-life problems. Oh, okay, maybe let's put it this way. We look at certain form of the probability function or probability density function and try to study their behavior, like, for example, find the expectation, find the variance. And then, now we look at the real-life problem that we encounter, and then try to formulate, look at the problem, try to identify the problem using the random variable, and then see whether the behavior of this random variable related or belongs to one of those very popular distribution. All right, and an example is like this. I think like toss a coin, we got the number of heads in, let's say, toss 10 times. All right, so x is the number of heads in 10 tosses. So how does this x behave? So this can be described by a binomial distribution. All right, tossing a coin, why bother to toss a coin? All right, but this is a very important distribution. Why? Because a lot of the real-life problems you can consider as a trial of, consider as a sequence of experiments or sequence of trials. And each trial can have only two outcomes, success and failure. Now this is the beauty about it. You can define what is a success, what is a failure. Like toss a coin, getting a head may be a success. But I can also define, for example, I'm not interested in head and tail. I just interested in where the coin lands from a reference point. So suppose it's continuous, you measure the distance, right? But now I define it. Okay, I define a success if your landing point is 5 meters away from a reference point. If the landing point is shorter than that, it's considered a failure. So now I change the question into just a success or failure. What is a success? When the coin lands 5 meters away from a reference point. But if it's shorter, then it's considered a failure. So I can always dichotomize. So like your test results, okay, not test yet, but let's say your test result may be range from 0 to 100 marks. So a lot of numbers. But I can set it as pass and fail, right? So that if you got easy test set as 60 marks, it's pass. Then you got 60 and above, you are success. Less than 60, failure. So I can dichotomize it. Or maybe the test is too hard. I set it as 40 as a passing mark. So a success will be considered as x bigger than 30, bigger than 40, and then less than 40 is considered failure. So this kind of ways is very useful. So what we're going to discuss is, okay, I look at the behavior of all these common distribution to a number of them, and then your job is to try to link up a real life example to these common distributions. All right? So that's what we are going to do in chapter 4. One very common distribution is normal distribution. You have to know how to use this distribution, or the behavior of this distribution, and how to use this for your problem. Okay, so these are the common distribution that we are going to discuss. Discrete uniform distribution, Bernouin distribution and binomial distribution, negative binomial distribution, Poisson distribution, and we try to link this to this. All right. So a Poisson distribution, binomial distribution can be approximated by a Poisson distribution. Now, for all these distributions we are going to discuss, you know, first of all, what does the random variable mean? Secondly, how is it behaves? So usually the distribution will be described by some unknown, some constant, some constants. We call it parameters. So like, for example, Bernouin distribution, it depends on a parameter called P, which is the probability of success. Binomial, there are two parameters. One is the number of trials. The other one is the probability of success. Negative binomial also, there are two parameters, the number of successes we want, and P is the probability of a success. Poisson has only one parameter, depends on one number. Usually denoted by lambda. It basically is the expectation of the random variables. But anyway, we are going to discuss it. So for continuous, we are going to talk about continuous uniform distribution, the exponential distribution, and the normal distribution. And how we are going to approximate a binomial distribution using normal distribution. All right, so discrete uniform distribution, very simple. This is the random variable x, and in order to talk about distribution, you have to know two things. First of all, the probability function. Second, the range of the x values. So in this case, the x values is x1, x2 up to xk. All right, just have k numbers. And then, so you have f of x evaluate x1, f of x evaluate x2, all this. And because it's uniform, which means that it's all the same. It doesn't depend on which value. No matter whether it's x1 or x2 or xk, all have the same probability function. So what should it be? So each one have equal probability. So this must be 1 over k. So a uniform, discrete uniform distribution will look like this. F of x equal to 1 over k. For x equal to x1, x2 up to xk. Can k equal to 1? That means instead of a k value, can I have just one value? What does it mean if you have only x1? If you have x1, then what is f of x? The probability 1, right? So what does it mean? It means you don't have a random variables. You don't have a variable because it's only one value, no variable. Not only that, it's no random. It must be x1. So in that case, it's not considered as a random variable and no distribution. So what it means is that at least you have two values. You must have two values. Two or more values. All right? Okay, so now we are going to do all this. For all the distribution, you have to work out these two numbers or have some idea. So the first one is the expectation of x. The second one is the variance of x. So for this, the mu is just the average of all the x values. All right? You sum up all the xi and then divide by k. And the second one is the variance. So the variance is each xi minus mu, square it, and then take the average. Now, some of you may confuse. Then should I divide by k minus 1 or should I divide by k? Remember, this is the population. We're talking about the population. So it has to divide by k. Your k minus 1 is only for applied to a particular sample taken from a population. You're talking about the sample variance. Then you divide by n minus 1. Here, you have to divide by k because that k value, you take the average. Right? Because it follows from this definition. And each of this one is 1 over k. All right? So it looks as if you just sum up xi minus mu square for all the xi and then divide by k. And this is just applying this formula for the variance of x. So you just square each individual value and then sum them up, divide by k, and minus mu square. So here's an example. We have 4 light bulbs. So I select one from this one. So the probability is equal for each sample, each light bulb. So it's 1/4 for each value. All right. So this is the probability function, and you can work out the expectation and the variance. But in this case, not too much meaning. All right. Here's another example. I have a sample space 1 to 6 with probability 1/6. So they are uniform distributed. This is this distribution can be used to model your toss a die with 6 outcomes, equal likely. All right, so we can work out the expectation is 3.5. So you expect outcome equal to 3.5, and the variance is 35 over 12. All right. Okay. Binomial distribution. Okay, let's leave it for next week, next Monday. All right, for binomial distribution. So we stop here.